All right, so now we're going to actually move on from Monte Carlo algorithms to Monte Carlo metropolis algorithms. And so what we're going to do is we're going to solve a simple problem. And that problem that we're going to solve is, let's say you take a random number of electrons, free electrons, and put them onto a conductor. What shape will they take on that conductor? Now, maybe you think this is a trivial one, and maybe if you pay attention during physics class, you'd know that the excess electrons go to the edges of the conductor, which is exactly what they do. But what we're going to do is we're going to do that using a Monte Carlo metropolis algorithm. And so what you see is with Python, what I did is I made a quick script that takes, first we import numpy as MP, then we set some constants, k, which is 9 times 10 to the ninth in SI units, and E, which is the fundamental charge of electrons, which I'm not actually going to use. it's all for show. And then lastly, what we'll do is we'll ask the user how many charges they want to simulate, and that's where the input comes in. Again, if you're using Python 2, or the plugin raw input for this instead of input, difference between Python 2 and Python 3. And then next thing we'll do is we'll use actually NumPy to make a random array of positions for those charges. And so pos or POS is equal to np.random.rand. And of course we're going to give it the number of charges, and it's going to have columns equal to 2. So it's going to have x and y. We could do this in 3 dimensions if we wanted to. We would have to add a third column. Easy enough to scale that up. The next thing we're going to do is we're actually going to define a new function, and that function is going to actually calculate the energy between each position. Again, this scales easily if we wanted to go to 3 dimensions. And so get energy, we'll take that position array, and what we'll do is we'll set energy equal to 0, and then we'll just iterate through each charge. And so we'll start with the first charge, and we'll go through each charge in the position array. And the first thing we'll do is we'll get the actual location of that charge. We'll take the difference of that charge, and I actually now realize that we're actually going to double count here. So here what we're going to do is do CSUM. The CSUM is going to be the sum of the reciprocals of the squares of the difference matrix that aren't, again here using logical indexing, difference not equal to 0. I realize we're actually going to count twice each one we get. And so actually what we need to do, we're going to double count. So what we should do is just divide this by 2. I think it should be fine. Okay, so because what we're actually doing is we're taking the first charge, getting the difference, adding the sum of the square reciprocals, and then we're taking the second charge, adding the sum of the square reciprocals. That includes the one we've already calculated. And we'll do that as we go. We actually only need to do half as many calculations as we need to do, because you don't need to do 1, 2, 2, 1. You only need to do 1, 2. So actually the energy we calculate is half the total energy we're calculating here, and so we'll just divide by 2. That's fine. And so the last thing I'm going to do is print off for the user. And so if you run get energy, nope, energy calc, how many electrons, we'll do 10, and that's what we get for the energy. Of course, this is not scaled by either k or the fundamental charge electron, so obviously we should multiply the total energy by E squared and by k to get the total energy in terms of joules. But now what we want to do is we actually want to do Monte Carlo or metropolis. So if we do import matplotlib.pyplot as plt, get plt.scatter of pos to do 0, sorry, we have to do all 0, and then pos that one. And oh, what does it do? This is my new like Python spider experience. What did it do? This is so bizarre. Can you open this? Okay, so we can make a scatter plot if we wanted to. I don't know why it doesn't open in the freaking window. Oh my gosh. Here, is this open a window? He's always making a window. Okay, we can see the plot. So obviously what we want to do is we want to visualize the plot, a scatter plot of the XY positions of each electron. So you can see here, if these two electrons are close to each other, that's going to be a high energy. We want them to be far away as possible. So the next thing we want to do is we actually want to minimize this. And so what we'll do is we'll set current best equal to pose. And then we'll do a for I, or let's do j. Range, we'll do 1,000 iterations. And what we'll do is we'll make a new position. And that new position will be new pose is equal to np. And I can just copy this. So it's new random position. And then we'll do new energy equals get energy of new pose. And so if new g is less than energy, then current best equals new pose. And we don't need an else statement. We don't need anything else. That's basically it. And we'll let it run. And so what I'm going to do is I'm actually going to find this and do this as energy. So it's only going to print the energy out once. It's going to print the energy at the very beginning of the loop, and then it's going to basically define current best is equal to pose. So again, it's only going to update the current best positions for the electrons as the energy actually is lower. So here it's going to check if the energy is lower, it's going to record that as the new best. Obviously, it's going to have terrible sampling, but we're not too worried about that actually. So we do 100. Oh my gosh, that's going to go forever. Let's do 10. Okay, so now if we do pose current best. Okay, so I figured out my problem. My problem is that I didn't save. So I have to save it first, and then what I'm going to do is I'm actually going to do 4 electrons. So obviously 4 electrons should go to the corners. And so once I save this, and I can do with 4 electrons, I can do a bunch of times. So if I run energy calc with 4 electrons, it's going to take a while. Obviously, I told you, sampling is going to be terrible because obviously it's terrible sampling. Because again, it's randomly generating positions. So it's not like it knows sort of what the best outcome is and just goes right to it. It's trying haphazardly, generating random numbers to come up with a better solution. So it's sort of fumbling in the dark. And so, yeah, this is a terrible algorithm. But this is Monte Carlo, right? So this is Monte Carlo using random numbers to come to a better, more informed decision about things. And so you can sort of see with 4 positions, so we have a large x value, a small y value, right, which is the lower corner. We have a small x value, large y value, which is that corner. We have a medium, so it's actually sort of down here. And then we have a large x, small-ish y, so here. Again, we can do scatter of current best 0, and this is not going to be what I want because It's going to be dumb. I don't like how Spider is doing this now. Oh, actually, that's nice. Okay, so that's kind of where they are. And I'm going to add that right to my script. So when it's done executing, you can run this. And I need to import matplotlib as, let's see, dot pyplot. Okay, that should work. Okay, cool. So if I do this again, save this. I did save this. From matplotlib import pyplot as plt. That's what I have to do for that, and we'll do 4, and then here's what it does. Okay, so we have a low minimum energy, and then of course it's getting closer to the edges, right? I can do it more times. It's going to take a lot more time to simulate. So if I actually wanted to do this, and you should do this actually, if you want to actually see the power of Monte Carlo Metropolis, is sort of directed simulation. If I did 3, it'd probably be a lot quicker. But I'm lazy, so I'm trying to do 4. So if we do 3, it should hopefully be right at the corner, like the triangle. Yep, that's what you expect. So it's exactly what you expect. If I do this more times, we should see it get even closer. But it's obviously hard to do that because of how many times it has to run. Again, fumbling in the dark to try to figure out where they should be in order to minimize the energy. So Monte Carlo is not the best way of doing things. But if you have another way, if you have no idea what's going on between the different variables, again, here we kind of have calculations, and we know sort of from physics where they should be. But I should also print out the maximum energy, but oh well. Here we are. So I hope you enjoyed this scientific programming with Python episode using Monte Carlo and sort of doing an energy calculation. And it's been fun. I really enjoy this this particular simulation because I think it's really interesting, especially if you let it run for a while. It gives you pretty interesting results. And so you can see like how 5 or 6 different electrons will orient themselves from a square plate. So enjoy, have fun with it. That's the important thing, I think, really. Hope you learned something today.